Single-phase induction motors are a type of AC motor. They are widely used in residential and light industrial applications. Unlike their three-phase counterparts, they operate on a single-phase power supply. This makes them suitable for places where three-phase power is not readily available. Examples include household appliances, fans, and small pumps. These motors are known for their simple construction and reliable operation. However, they exhibit lower starting torque compared to three-phase motors. This characteristic necessitates special starting mechanisms. These mechanisms create a rotating magnetic field to initiate rotation. The popularity of single-phase induction motors stems from their affordability and ease of maintenance. Their robust design ensures a long lifespan, making them a cost-effective solution for various applications. Understanding the working principles and characteristics of these motors is crucial for selecting and utilizing them effectively in different applications. A single-phase induction motor comprises two main parts, a stator and a rotor. The stator is the stationary part and houses the main windings. These windings are typically made of copper wire and are wound around a laminated iron core. The iron core enhances the magnetic field generated when current flows through the windings. The rotor, on the other hand, is the rotating part. It sits inside the stator and is mounted on a shaft. Unlike the stator, the rotor doesn't have any windings in a simple squirrel cage type. Instead, it consists of aluminum or copper bars placed in slots around the periphery of the rotor core. These bars are short-circuited at both ends by end rings, forming a cage-like structure, hence the name squirrel cage rotor. The interaction between the rotating magnetic field produced by the stator windings and the induced currents in the rotor bars generates torque, causing the rotor to turn. The stator and rotor are separated by a small air gap, which is crucial for efficient motor operation. The size of this air gap is carefully designed to minimize losses and maximize performance. The operation of a single-phase induction motor relies on the principle of a rotating magnetic field. However, unlike three-phase motors, where the three-phase windings naturally produce a rotating field, a single-phase supply creates a pulsating magnetic field. This pulsating field alone cannot start the motor. The double revolving field theory explains how this pulsating field can still induce rotation in a single-phase motor. According to this theory, a pulsating magnetic field can be represented as the sum of two rotating magnetic fields. These two fields rotate in opposite directions but with equal magnitude. When the stator windings are energized, these two counter-rotating fields induce currents in the rotor bars. Each rotating field interacts with the induced currents to produce torque. Since the fields rotate in opposite directions, the resulting torques are also in opposite directions. At standstill, these opposing torques cancel each other out, resulting in zero net torque. This is why a single-phase induction motor cannot start on its own with only a single winding. However, once the rotor starts rotating even slightly, one of the rotating fields becomes dominant. This happens because the rotor's rotation relative to the rotating fields changes. The dominant field's torque overcomes the other, and the motor continues to accelerate until it reaches a speed slightly less than the synchronous speed of the rotating field. The difference between the rotor speed and the synchronous speed is called slip. The performance characteristics of a single-phase induction motor can be analyzed using an equivalent circuit. This circuit represents the electrical behavior of the motor in a simplified form, making it easier to understand and analyze. The equivalent circuit of a single-phase induction motor is similar to that of a transformer, with the stator and rotor windings represented as inductances and resistances. The stator circuit includes the stator resistance, R1, stator leakage reactance, X1, and a magnetizing branch. The magnetizing branch represents the excitation current required to produce the magnetic field and consists of the magnetizing reactance, Xm, and a core loss resistance, Rc. The rotor circuit viewed from the stator side includes the rotor resistance, R2, rotor leakage reactance, X2e, and the slip-dependent rotor resistance, R2 per S. Determining the parameters of this equivalent circuit is crucial for predicting motor performance. These parameters can be determined through various tests, including no-load test, conducted with the motor running at no load. This test helps determine the core losses and magnetizing reactance. Locked rotor test, performed with the rotor physically locked. This test provides information about the stator and rotor resistances and leakage reactances. DC resistance test. This test measures the resistance of the stator windings, which is used to calculate the stator copper losses. By analyzing the data obtained from these tests, engineers can determine the equivalent circuit parameters and use them to predict motor characteristics such as torque speed curves, efficiency, and power factor. Section 5 Split-phase starting methods. As previously mentioned, single-phase induction motors lack starting torque due to the pulsating nature of the magnetic field. To overcome this limitation, various starting methods have been developed. These methods aim to create a phase difference between the current flowing through the main winding and an auxiliary winding, resulting in a rotating magnetic field that can start the motor. One common method is the split-phase starting method. This method utilizes an auxiliary winding with fewer turns and higher resistance compared to the main winding. This winding is connected in parallel with the main winding during starting. Due to the difference in resistance and reactance, the current flowing through the auxiliary winding is out of phase with the current in the main winding. This phase difference creates a rotating magnetic field, albeit weak, which is sufficient to start the motor. Once the motor reaches a certain speed, typically around 75% of its rated speed, a centrifugal switch disconnects the auxiliary winding. The motor then continues to operate on the main winding alone. Section 6. Applications of single-phase induction motors. Single-phase induction motors are widely used in a variety of applications, particularly in residential, commercial, and light industrial settings. Their popularity stems from their simple design, low cost, reliability, and ease of maintenance. Some common applications include household appliances. Many household appliances such as refrigerators, washing machines, dryers, fans, air conditioners, and vacuum cleaners utilize single-phase induction motors. These motors provide the necessary torque and speed for these appliances to function effectively. Pumps and compressors. Small pumps used for water supply, drainage, and irrigation often employ single-phase induction motors. Similarly, small air compressors used in workshops and garages also utilize these motors. Fans and blowers. Single-phase induction motors are commonly found in various types of fans, including ceiling fans, exhaust fans, and industrial blowers. They provide reliable and efficient operation for these applications. Tools and machinery. Power tools like drills, saws, and grinders often use single-phase induction motors to drive their cutting or grinding mechanisms. These motors provide the necessary power and torque for these tools. Section 7. Advantages of single-phase induction motors. Single-phase induction motors offer several advantages that make them a popular choice for many applications. Low cost. Compared to other types of AC motors, single-phase induction motors are generally less expensive to manufacture. This is due to their simpler design and the use of fewer materials. Simple construction. The construction of single-phase induction motors is relatively simple, making them easy to understand and maintain. This simplicity also contributes to their lower manufacturing cost. Reliable operation. These motors are known for their reliable operation and long lifespan, especially when properly maintained. Their robust design can withstand harsh operating conditions. Easy maintenance. The simple construction and lack of brushes or commutators in squirrel cage types minimize the need for maintenance. Regular lubrication and cleaning are usually sufficient to ensure smooth operation. Section 8. Disadvantages of single-phase induction motors. Despite their advantages, single-phase induction motors also have some disadvantages. Low starting torque. One significant drawback is their relatively low starting torque compared to three-phase motors. This limitation necessitates the use of special starting mechanisms, which can add complexity and cost. Lower efficiency. Single-phase induction motors generally have lower efficiency compared to their three-phase counterparts. This means that they consume more power to produce the same output power. Pulsating torque. The pulsating nature of the magnetic field in single-phase motors results in pulsating torque, which can lead to vibrations and noise. This can be a concern in applications where smooth operation is crucial. Sensitive to voltage fluctuations. These motors are more sensitive to voltage fluctuations than three-phase motors. Voltage drops can significantly affect their performance, leading to reduced torque and speed. Section 9. Conclusion. Single-phase induction motors are essential components in various applications, particularly where three-phase power is unavailable or impractical. Their simple design, low cost and reliability make them a popular choice for powering a wide range of devices and machines. Understanding the operating principles, constructional features, and performance characteristics of these motors is crucial for selecting and utilizing them effectively. While they offer advantages such as low cost, simple construction, and reliable operation, it's important to consider their limitations, such as low starting torque and lower efficiency, when making design choices.